This presentation shows the result of the AIXM compression benchmarking, an OWS activity led by Jérôme Jansou from Atos Origin and Thibaut Dacla from Atmosphere. Let's start with giving some context. While the aircraft is on the ground at reasonable speed, the communication is not a problem. The bit rates are high, so the volume or the format of the data are not a problem. But when the aircraft reach a certain altitude or a certain speed, the problem is different. To communicate, the aircraft has to go through the data link, that is either VHF or SATCOM. But on this data link, the bit rates are falling drastically. The access to broadband data link with higher bit rates remains rare. This fall of the bit rates doesn't allow the communications to be done in the same format as they were on the ground. This is why there is clearly a need for efficient compression, and this is what is studied here in OWS-8. For this activity, the benchmarking environment was the Java platform JAPEX, slightly modified to allow additional measures. In this study, several candidates were benchmarked, including FastInfoSet, Exefficient, RowDeflate, and WXML. The studies focused on three main criteria, which are compaction, memory footprint, and CPU consumption. To study those candidates, 4 families of test files have been created. The first family is composed of digital NOTAMs files, which are small files with a size below 10 kilobytes. The second family is composed of bigger AIXM files with size up to 1 megabyte. They are mono feature files served by the Snowflake WFS. The third family encompasses even bigger AIXM files with size from 1 up to 20 megabytes from various sources. And finally, the fourth family is made of technical files, which have been crafted with a focus on different specific points. Here are the compaction results for the first family of dNOTAM files. While the RowDeflate reduced the size of the files down to 30%, the EXI compression algorithms allows to go down to 13%. So in that specific dNOTAM case, the EXI with schema knowledge and deflate post-compression, here shown in black, is 3 times more efficient than the RowDeflate. Regarding the results on the bigger file from the 3 others families, the following points have been assessed. The compression efficiency is very much dependent on the feature type. On bigger files, EXI only performs up to 50% better than RowDeflate, while it's a much more complicated algorithm. EXI can reduce the size of the floating points through grammar knowledge. However, the deflate post-decompression performs worse on this reduced size information than on the actual original ASCII. So EXI and deflate post-compression are not really working together, but more one against the other. End of the day, overall performance is identical between RowDeflate and EXI on big files. Regarding the different levels of compression in the RowDeflate, it has been assessed that going up to the level 5 or 6 is enough. Indeed, as shown in the graph, the difference of compactness between level 5 and level 9 is almost negligible, while level 9 is much more complex than level 5. EXI is quite a heavy compression algorithm. Indeed, as shown in the graph, its memory consumption, for instance, is much higher than the other algorithms. EXI can spend several megabytes to build its grammar, and this might represent a problem when it comes to data link communications. Finally, FastInfoSet, although not being the most efficient in terms of compactness, is clearly the fastest algorithm of all, which can represent an advantage on ground systems. And here is a summary of the conclusions drawn from this study. We have seen that EXI is the most efficient way to compress digital NOTAMs. This is clearly efficient for data link small bit rates. When we consider bigger files, RowDeflate and EXI are identical in most cases. FastInfoSet, although not being the most efficient compression algorithm, is by far the fastest, and that can be interesting for fast ground networks. With regard to AIXM, the next step for improvements would be to improve deflate post-compression and make it work in a better way with EXI, to work on the AIXM schema, for instance removing unnecessary or redundant data to improve compression, and to go for a better handling of the coordinates, which represent most of the AIXM files, with methods such as differential storage or variation of the precision depending on the feature. More complete and precise information can be found in the ER AIXM performance assessment.